So you have the next project reports here, right? For the homework assignment too, some of you didn't turn in your homework assignment too, right? So, and some of you got pretty low score. So if you have any concerns, talk to me, right? So one of the things I did last semester, since we have so many grading points, I let each one of you have one of the lowest scoring ones, the grades replaced by the average for that particular stuff, right? Because there's so many data points. If you have one particular stuff you didn't turn in, or one particular stuff you kind of went off or something, right? But I was only going to do one. So if you have any problem, talk to me now so we can deal with it now rather than at the end when it's kind of hard to go back, right? And similar thing for the projects. If you're a project partner and you are not seeing eye to eye and there are issues, we'd rather deal with it now than at the end when you're kind of stuck with the grades, right? So how was your experience with writing the matrix code for the project? In terms of what the operating system is involved, right? It's only involved with the thread create or whatever locking mechanism you used. Like those calls are the ones that the OS would care about, OS would talk about. How you program the exact functions, how you write the code is entirely up to you, right? And I've seen like code which works, but you can imagine as you add more threads, as you scale this problem, it becomes more horrendous, right? So one of you was concerned about how to pass argument to the thread in a global variable and have the thread take the value before you start the new thread, right? So they were doing something like, let's say, value dot arg1 equals something, arg2 equals something, right? You do a thread create in a loop, right? So this means that you set these arguments, you call the thread create, right? But there's nothing which says the thread has to run immediately. I mean, you don't know when the thread is going to run. So if the loop comes back again here, right, you'd overreturn these values with the new set of values, right? And then the old thread would get the new values while you enter it to have the old value, right? How many of you ran into some problem like this, right? So one of the ingenious solutions I've seen for doing this is to lock some variable, right? And inside the thread, unlock the variable, right? That solves this problem. I mean, I can tell you who it was if the person doesn't mind, but basically this lets you kind of make sure that after the thread is fully ready to give the values back, you can lock this stuff, right? This solves the problem, but it's a horrendous piece of code, right? Because now you have this lock and you have this unlock somewhere here. So you have another function here where there's a unlock randomly, right? When you write code, I mean, one of the stuff that you will realize when you go for a job or something is you write code that you hope to use for more than a few weeks, right? So if I ask you after a year and say, why is this unlock here, right? You tend to forget because there is very little which says that this lock is related to this unlock, right? So you end up having this unlock code where a year down the road, you don't know what this unlock is for, so you either get rid of it or change the semantics and you get horrendous bugs, right? How many of you ran into cases where your program was kind of getting into deadlock or doing something weird and you tried to use a debugger? So one person who used a debugger. So what debuggers do you guys know how to use? What debugger have you used in the past?
I used Xcode.
I'm sorry?
I was using Xcode.
Okay. What debuggers do you guys know?
We don't usually use them.
I've never used one of those.
They're really small software.
How do you debug your programs?
Print off. We use the Visual Studio debugger, but when we're on Linux, most of us don't bother.
Okay.
GDB is a good one, but it's really not intuitive to pick up when you first start using it.
it'll return like all kinds of great information to you, but unless you know how to pass all the arguments to it, you won't get anything useful out of it.
But the simplest debugger, right? The simplest debugger should let you set a breakpoint, right? So should let you stop some execution at some point and let you look at what the variables are, right? I mean that whatever you do, except for printf. In printf, the programs just go off. But any debugger, Visual C or JDBA something, it ought to let you stop your program and look at the state, right? Now imagine what happens when you have multi-threaded programs, right? You have to stop one thread at a time, right? Because you can't interact with all the 4 threads at the same time unless you have like octopus hands or something, right? So you only look at one thread. So when you have 4 threads going through, right? And you have no idea what this particular thread is doing, and you stop this, and you're single stepping through, right? That does nothing to the other threads. I mean, they go off, right? So it's worse than letting them go by themselves, because at least if you let them go by themselves, this would at least try to keep up with the other ones. Now this thread is like kind of lagging behind. The other threads are moving forward and making progress. So debugging this is horrendous, right? That's not OS's problem. That's somebody else's problem, right? I mean, just like you guys should know debuggers, and I don't know which class would cover that. Right? Same with the whole notion of this module. I mean, there's a whole lot of stuff we study, but OS is only concerned with giving you these primitives, and it's up to you to figure out how to code them, right? And so imagine what happens when you go to a distributed model, right? All the stuff you're talking about applies exactly to a distributed system. Distributed systems are basically a bunch of computers which are separate computers, and they're trying to talk to each other. Same thing like what you have in your multi-processor systems, except the network is far off. So you have one computer here, one in my office, and so on, right? So we have the Bob cluster at Notre Dame with 1,000 processors or something, right? So you have 1,000 processors, 1,000 or so processors, and you can use all of them to write your code, right? And they're all in different machines, but from a program perspective, it does not matter whether the machines are in the same motherboard or kind of far off, except for the timing. So when you do in a distributed system, and you have all these machines, all the stuff you're looking at in terms of deadlock avoidance and stuff it's much harder, right? Because deadlock avoidance needs to know how many resources you want and how much the system has. When you have 1,000 nodes, somebody has to get all this information, make a decision, and give say you can go, right? So the deadlock avoidance says, at some point, somebody has to decide, can I allocate the resource, right? And in a single machine with two processors, it's sort of easy to think of. But if you have 1,000 machines, all of them have to, every time they want to allocate resource, they have to come and ask me, can I do this? I have to keep a state of the whole system. The whole system operates in lockstep at the way, the slowest node. So that becomes even more complicated, right? So these are pretty complicated stuff, but if you want to go into any kind of serious computing, you are kind of forced into this either because of dual core or because of the multiple distributed systems, right? So we have one of our Notre Dame alumni from Microsoft. I think he's been there for like 15 years or something. So he agreed to come to our class on Monday to give a sense of how Notre Dame, education helped them at Microsoft and stuff. And I was hoping to have him give you a sense of how many of these things apply, right? So if you have any questions, he'll be here on Monday, right? And many of you may want to go to summer internships or something with Microsoft, and that's a good way to talk to him. So are there any questions? So was the project helpful in making some of this stuff clearer, right? And I hope you understand that the notion of critical section is, even though we talk about it as a pretty clear concept, right? In this particular example, the critical section is somewhere from here to here, right? Somewhere from where the thread create happens, and inside the thread is where the critical section ends, right? So as abstract concept, it looks kind of bizarre because the critical section starts in one thread and ends in another thread, which will be created inside the critical section itself, right? But that's entirely up to your logic, and that's why things happen, right? So we were in the last class we were looking at deadlocks, deadlock prevention, and deadlock avoidance, and one of the things we mentioned was most of the operating systems don't deal with deadlocks because it's so horrendous, and if you have to deal with them, then it slows down your program because you have to make this decision. You have to be constantly on guard every time I want to allocate a resource, right? So maybe not for your laptop or desktop, but for real computing where people spend a lot of money, these are issues that you want to be aware of, right? So there are a number of ways to. So the way you prevent deadlock is you make sure that the 4 conditions never happen, right? And that's too strict because your programs may never actually, I mean, it may look like they may violate, but they may never actually violate. So with the notion of deadlock avoidance, you let the system go, even though you know the current allocation is unsafe. I mean, in the worst case, it's unsafe, but you let the system go as long as the system is safe, even though it could be potentially unsafe. And at the first instant that it looks like it's going to go unsafe, you do something, right? So deadlock avoidance is a little bit easier than deadlock prevention because you still let the system go for a bit and try to avoid deadlocks. And one of the classical solutions to this problem is the banker's algorithm, right? This was designed by Dijkstra, I think in 60s or something, right? So essentially, this is modeled after how a bank would operate, how a banker would give loans to you, right? So assume that all of you have a credit limit, and let's say all of you have credit limit of like 500, right? The banks never have enough money to service all of you if you use all of your credit limit, right? So if everyone who has a credit card fully maxed out the card, then the banks will go bankrupt, right? Because they don't actually have that much money to give away, but they know that people on average how much money they will ask for, and then they do this magic so that things sort of work, right? But if all of you ask for all the money, the bank will crash, or in our parlance, it'll go into deadlock, right? So if all of you took out the money, then I've given enough money to all of you that you can't complete because you want all the money, right? But the bank does not have any more money to give anybody. And since I can't take the money that I gave the bank cannot take the money back from anybody that they gave, right? The bank cannot, so you get into deadlock, right? It's not similar to the actual case because actual case, the banks have so much money that you rarely go into a condition where you run out of money. Plus, people pay interest, right? There's no concept of interest here. So even if you're deadlocked, the bank can wait for you to start collecting interest and then eventually pay up, right? But as a concept, that's the goal, right? So it's potentially unsafe because if all of you ask for the money, we'll get into deadlock. But the bank wants to give you money such that there is one safe path for things to get out, right? For this to happen, the bank cannot have less money than any customer whose credit limit is more than what the bank has, right? That cannot be solved. So if the bank has $1,000 and if your credit limit is $2,000, then the system cannot guarantee to be deadlock free because you're going to want 2,000. The bank does not have 2,000, so it does not work, right? And it also depends on the fact that you can tell how much you're going to ask, and that's the notion of credit limit in case of the banks. And here, when a process comes, it has to say how much money, how much resources it would need, it has to know how much you already been allocated, and it has to know how much you could potentially ask, which is the difference between what is allocated and what you really want. And based on that, you can every step of the way you can figure out if it gives you the resource, right? Is there a possible way for the things to get out, right? If there's no possible way, then then you have to wait till the corresponding processes finish and then give the resource back. Right? So one of the side assumption is all the processes would eventually finish. If they don't finish, then the system does not work, right? So the system has a number of data structures to implement this stuff. So the first one, so if you assume n processes and m resources, right? So you need to have vectors or arrays because you have that many resources, right? So the first vector you have is the available vector, which says how many of each resource the system has, right? So that gives the maximum count of resources that the system has. So in case of the bank, that's the amount of bank that the money has, right? And so the next array is max. Max says how much each process would ask of the system. So that's the credit limit in the bank parlance. And the next notion is allocation, which says how much was allocated to you, right? So you have the notion of how much resources there are in the system, how much each process would request, how much of the request is currently allocated to a process, and if you subtract it, you get the need, which says how much you would ask in the future, right? So you have to maintain all these data structures to figure out how this stuff happens. And again, this algorithm cannot be used if you can't know how much resources you would want in the future, right? Or during the entire run of the system, right? So the system has two components. One is the safety algorithm, which tells you whether the current state is safe, right? So the way the algorithm works is, if you want a new resource, it pretends that it's going to give you the resource, and then it checks if the new state is safe. If the new state is safe, then the resource is given to you. If the new state is not safe, then the resource is not, then it undoes whatever it tried to give you, and then you have to wait, right? So the safety algorithm is the crucial step, which figures out if this potential new state is safe, right? So for a potential new algorithm to be safe, you have to figure out all the combinations of resource allocation such that everybody else can finish. So the assumption is, I give you this resource, you ask for a resource, I give you the resource, and then I have to see, given the rest of the resources and what everybody can potentially ask for based on the need array, if they can finish, right? If they can finish, then I can let you go, right? So I'm not sure if I want to go through the code line by line. So essentially, you try to so you set all of them to finish to false, right? Then you try to find all possible combinations such that the particular process hasn't finished, and whatever it's requesting can be less than whatever I have working, right? So I start out with whatever the total available resources, and then I start giving out resources to people. So I look for cases where what you're requesting is less than what I currently have. If in 2B, right, if what you need is more than what I currently have left over, then that means this is unsafe, right? Because I cannot service you, so we cannot finish, right? So this algorithm does not look into the case where the process could finish sooner and return the money or return the resources, right? So it's trying to figure out, if nothing else changes, can all these things finish, right? So it's pessimistic, because in real case, some of the processes which already had the resources could have released the resource in the future, but they don't. I mean, it's not we're concerned about that. It's trying to make sure that the system would never deadlock, right? So the second step, it tries to figure out, find all the possible combinations, try to give them the resources, and see if they finish. And at the end, if you're given the resource to all the processes, right, that means all of them can be serviced, so the state is safe, right? So is that the high-level description clear? So when you want to do a resource request, this is sort of the how you do it, right? So essentially, when you ask for a resource, right, it first makes sure that it first makes sure that whatever you're requesting is less than what we currently have. If you ask for more, this cannot be serviced, right? So then essentially, I allocate the resource to you, check. I pseudo allocate the resource to you, check the state of the new system, see if it's safe. If it is safe, then the resource is allocated to you, and the amount of resources I have goes down. If it's unsafe, then you put the process to wait, you undo what you did, right? So every time you do a resource, you have to run this algorithm, and the safety check algorithm is pretty expensive. Depending on how many states you have, it's pretty expensive because it's trying to find all possible combinations. And you want to come in?
She's one of the Spring Viz students.
Sure. You can. This is.
Oh, I'm good.
Okay. Hi. So essentially, So once you run this algorithm, so every time you ask for a resource, I have to run this algorithm to see if it's a safe state, right? And the safety algorithm is not cheap, right? So there are a lot of reasons why this algorithm is not really used, because you have to know how many how many resources you need. It's overly pessimistic because it does not assume that any of the processes can complete in the middle, right? It will make sure that deadlock does not happen, but in a real system, it will slow down the system a lot, right? And here's an example run of how the Banker's algorithm would work, right? So we have 5 processes, P0 to P4, and it has 3 resources, A, B, and C, right? And the system, when it started out, it had A, it had 10, and B, it had 5, and C, it had 7, right? So the 3 matrices, allocation says how much was allocated to the process, and max says how much you would potentially ask for, and available says how much of the particular resource is left, right? So for example, if you look at resource A, right? So if you look at the allocation matrix, P1 has 2, P2 has 3, and P3 has 2. So if you add them up and subtract from the total available, that's the currently available resources, right? So currently available resources 3 and 3 and 2, and as you can imagine, at this point, the max says how much they really wanted. So if for example, if P0 comes in and asks for 3 resources, asks for 7 resources, which is what it wants, right? If it asks for 7 of A, right, there is not that much in the system. The system only has 3, right? So it has to wait for some processes to finish, right? We know the system is safe because the maximum resource somebody can ask for A is P2 when they're asking for 9, right? Which is still less than the 10 the system has. So there is a way to get out, but you have to make sure that it may not be able to solve at the right current moment, but you can solve it eventually, right? So if you subtract the max and the allocation, this is the need graph you have. So essentially, you want the need to be so this is the amount of resources that each of the processes can request in the future, right? So I'm not going to go through the walk through the safety algorithm, right? But essentially, if you take this route, P1, P3, P4, P2, P0, if you take that particular route, the system is safe. Meaning, like, P1 gets to get all its resources. So P1 gets that's 1, 2, 2. It finishes, and then P3 gets all the resources it wants. Then P4 gets all the resources, and P2 and P0 and so on. And once you do the steps, the system, all the processes have finished, and all the resources have been allocated, right? So if you can't find such a state, then the system is unsafe, right? So here's a case where P1 is requesting 1, 0, and 2, right? And we currently have the same where we started before, right? So we started. So you're asking for 1, 0, and 2, which is less than 3, 3, and 2, where the system currently has. So you can still proceed. So it actually allocates to it, and the safety algorithm should tell you that P1, P3, P4, P0, P2 is a possible way for the system to get out, right? So you have to run the safety algorithm to show that there's that sequence which makes the system safe, right? And you can leave it as exercise to look at what happens if you ask for 330 and 020, right? So if P4 was asking for 330, look to the safety states to see if the system can succeed or not, right? So you have to actually work through the states, and if the particular allocation is safe, then it can be allocated. If not, P4 has to wait till the system state changes, right? Right. So this is one of the classical algorithms that you're supposed to know. There are a lot of practical reasons why it's never implemented. For the reasons I mentioned, that you have to know the future, and it's fairly expensive to find the safety states, right? But this is how you would go about doing this stuff, right? Yeah.
When you say request up there, does that mean need? Or which matrix?
No. So the need says that P4. When P4 came in, it said it wanted some amount, right? I forget what P4 was asking. So I think P4 was asking for 4, 3, and 3, right? Which says that P4 said, throughout the program, I may be asking for 4, 3, and 3. Right now, at this instant, P4 has been allocated 0, and 0, and 2, right? Which means that need says, at some point, I could request up to 4, 3, and 1, right? That's somewhere in the future. Request says, at this instant, I need 1, 0, and 2, which is well below what. Hang on, something is wrong. Because the need, yes, 4, 3, and 1, right? So, it's asked, oh, sorry. I'm sorry. Yeah, we are looking at P0 here, right? I was looking at P4. Yeah, we're looking at P0, right? So P0 says that throughout the program, it can still ask for 7, 4, or 3, right? So within that, the large limit, at this instant, it only needs 1, 0, and 2, which is less than what it could potentially ask for, right? So we know that the P0 at some point can still ask for 7, 4, or 3. At this instant, it wants 1, 0, and 2. And we are trying to see if I give you 1, 0, and 2, would the system be safe? If it's not safe, you'd be made to wait, right? But we did promise you that we'll give you 7, 4, and 3. So all we say is you have to wait till the system state changes, till somebody leaves or something. But at some point, I can let you go. But for now, you have to wait. Does that make sense? Okay. Right? So those are the deadlock prevention and the deadlock avoidance mechanisms. You either try to make sure that the system can never possibly get into deadlock because you make sure that the 4 deadlock conditions never happen, or you do the deadlock avoidance where you let it go, but every time you have to make sure that at this particular state you're still safe and not going into unsafe state, right? The other way is let the system go as it is, right? Let the system go into deadlock, and when the deadlock happens, you detect it, and then you do something about it, right? So, what is one naive way you would detect deadlock? How many of you ran into deadlock for your homework project? None of you? How would you know if a system is deadlocked? Naive approach.
Nothing would happen for a long time.
Yeah. Even though we say that starvation is not deadlock, but if your program just sits there and does nothing, right? For the most part, you know something is wrong. And what would you do if it happened? Restart the computer. You wouldn't have to restart the computer. You can just kill the process, right? Because the resources that you're deadlocking on belongs to you, not the whole system, right? So if it is something that the kernel is deadlocked, then you have to reboot the machine. But if it's your homework project, usually if you kill your project, you should be fine, right? So the recovery scheme that you do is like you restart or kill your program and things are fine, right? So in a more pedantic fashion, to detect that there's a deadlock, right? You have to do the resource allocation variant of resource allocation graph, where you see, so you remove the resources to show which process is waiting for what, right? And I'll show you in the next slide what that looks like. And then you try to find out if there are cycles which show that there's processes waiting. If there's a cycle in the graph, then you know that there's deadlock, right? And yeah.
I was going to ask you, in a real-time system, if you have there's like a navigation system or something, and a deadlock occurs, since you know that it has real-time constraints, would you be able to use like a timing mechanism to interrupt that?
Okay, so one of the reasons I don't talk about real-time systems at all in this course is real-time systems do not go well with logs, right? Because logs and semaphores and all the things we're talking about will tell you which order things happen, but they don't tell you when things should happen, right? Logs cannot guarantee that you will get the log in 2 seconds. Log can say you will get the log sometime, right? So the whole notion of the critical section is I cannot guarantee you when you'll get something, and I cannot guarantee you what your process happens, but I can guarantee you that your data is safe, right? Real-time systems have a different goal. For example, one of the classical examples is a nuclear power plant, right? Nuclear power plant, when it's melting, you don't care whether it's safe. You don't care whether it gives you the lock after 5 minutes or something. You care that within certain time bounds, things have to happen, right? So real-time systems do not use locks. If they use locks, they have to have a notion of, I need this lock in some amount of time. If I don't get it, right, you have to break the step. I mean, you have to figure out what's important, right? So real-time systems traditionally don't deal with locks, don't deal with threats and all those things, because so real-time systems don't care about performance, they care about predictability. They want to be able to say, if the reactor is melting in 43 milliseconds, we will start action, right? That's their goal, right? Because 43 may be mandatory. I mean, it may be the case that after 45 seconds, all is lost, right? So they don't really care about performance, they don't really care about utilization. They don't really care if this computer does nothing ever in its life, right? It can be running for 20 years doing nothing, but on the one instant when it's melting down, it has to do what it has to do within that time frame, right? And threats go entirely against it, so they don't deal with threats, right? Does that answer your? And you might have seen that. I mean, like, how many of you saw the performance of your program very predictably going? As you add more threads, things became twice, thrice, or whatever faster. Or or how many of you noticed things were not exactly what you expected? How many of you noticed things were not exactly as you expected? 3 or 4. So the rest of you got what you expected. As you add more threads, things became faster and faster.
Yeah. What if you added more threads than there were, of course, in the processor, it slowed down?
Yeah.
We had kind of a weird result where at 256 threads, our program ran faster than at either 512 or 128 threads. I don't really know why, but we're just playing around with numbers.
Okay.
I'd say if you have you'll see it that sometimes it'll go up if you have an odd number of threads that isn't equally divisible by the number of cores you have. But if you have like 4 cores and 8 threads, it runs faster than if you had 7 threads or 9 threads.
Mm-hmm. And debugging and trying to understand why this happens is not trivial at all, right? I mean, there's some interactions going on, and some of the tools I mentioned, gprof and all those things, will help you figure out how many locks are being happening and where the contention is, right? But figuring out why that happens it's non-trivial, right? I mean, it's not like I can say, oh yeah, 256, oh that makes sense, right? I mean, you have to live this program for a while and understand what's exactly happening to see where things are failing, right? And that's precisely not what you don't want that in the real-time system, right? You don't want to say, whatever, right? But hopefully now you appreciate like what happens for. So one of the if you buy Adobe Photoshop or something, right? Once you do some operations on your picture, it has to go ahead and do lots of CPU computation, right? So the faster your processor is, you expect it to go faster. If you have many cores, you expect your Photoshop to go. If you have 2 processors, you expect it to be twice as fast. You have 4, you expect it to be 4 times as fast, right? And I think the latest desktops should be 8 core, right? Intel sells 4 core, 2 of them, so 8 core, right? So you expect your Photoshop to work 8 times faster on that machine, 1 times on your normal machine, twice on your desktop machine, and so on, right? So, and that's not trivial, even though the customers expect or want, I buy 2 processors, I want the Photoshop to run twice as fast. Because Photoshop is Photoshop or some of these tools are the reason why you buy dual cores and stuff, right? If you're using your Internet Explorer, you probably don't really care about many, or if you're using Word or something, right? You probably don't care about these things. So writing those programs, debugging it, making sure that it operates on whatever kind of code you can throw at it and still get good performance, it's a non-trivial task, right? And I mean, the example you used is trivial. What they actually go through is like a lot more complicated, right? And the key here is it's an n-squared operation. So as you increase the number of resources involved in this process, it could exponentially the time increases, right? So here's the how you generate the wait for graph. So the over on the left is the resource allocation graph, where you have processor and resources, and to make life simple, all the resources, there are only one instance of resource, right? So P2 is waiting for R4, R4 is assigned to P3, right? So wait for graph, essentially you say P2 is waiting for R3, because it is essentially P2 is waiting for R3 via resource 4, so ignore that, and you look at the corresponding wait graph, and you try to see if there are cycles there, right? If there are cycles there, then that particular stuff is in deadlock, right? So with this model, you let the process go, and periodically, once in a while, you go and look at all the resources allocated and what the status, to see if there's a deadlock, and if there's a deadlock, you report it's a deadlock, right? And the more complicated version, which is very similar to your Dijkstra's, the Banker's algorithm, is when you have many instances of resources, right? And essentially, you run something very similar to the safety algorithm when you have a deadlock in the last one we looked at, right? So essentially, if you look at the code, it's very similar to the safety algorithm, and you're trying to see if any given state is safe, right? If any given allocation is safe. If it's not safe, then if particular resource cannot be allocated, then you have a deadlock, right? So essentially, it's very similar to the Banker's algorithm. So I'm not going to go into detail here. So essentially, you run this algorithm when you have more resources to see if the system is in deadlock, and if it is, then you declare it's in a deadlock, right? So I'm actually going to skip this particular graph. So essentially, it's very similar to your Banker's algorithm, and so in this particular case, this sequence, the P0, P2, P3, P1, P4 would get you out of the system, so the system is not in a deadlock state. So in this particular case, right, there is no way to get out of the system. So if you look at this particular request pattern, the system there's no safe state. That means the system is in deadlock, right? And the algorithm is very similar to the Banker's algorithm, so you should run it through a thing. So the next key is trying to figure out how often you should run this deadlock detection, right? So essentially, the system is running on its own, right? All the resource if you request a resource, it's allocated to you without actually stopping your system. So the question is, how often should you run this deadlock algorithm, right? Again, it's an expensive operation, so you don't want to run it every second or so. You want to run it every so often to see if the system is deadlock. How often do you expect the deadlock to happen, and in that time frame, you want to run this algorithm, right? To essentially see if there's any deadlock in the system, right? So what would you do when you're in a deadlock? Right, that's not of like what to do, right? So the simple case is to kill the whole system, right? Kill your process, kill everything, and hopefully it'll be fine, right? Hopefully it'll be fine, because hopefully that if you run the same process again, hopefully they won't come back to the same state, right? So you kill everything, start everything from fresh, and then you hope things will happen, right? Is that a solution you can always use, where you kill the process and hope everything will clear out? Tell me why that's not a preferable solution. So assume you have P1 is waiting for P2 and so on, right? And I notice that they are deadlocked, so I kill these two, right? Would that solve my problem? It'll solve my problem because the deadlock is no longer there, because the processes are not there, right? But what damage would this do?
You're not running P1 or P2 anymore.
Yeah, you're not running P1 P2 anymore, but what other side effect this would have caused? Yeah.
You'll have wasted all the time that process had spent executing, doing something.
Yeah, so
It's better to just kill one if you're going to do it.
let's say the P1 started here, right? And you killed it right here, right? All the stuff it did, all the CPU it used, and all those things are wasted, right? What other thing could have happened here? Yeah.
It could be in the middle of doing something,
Mhm.
and if you kill it, it'll leave something half finished
Mm-hmm.
or half changed.
Mm-hmm. Yeah. So if you're writing files, if you're creating stuff, right? I mean, you were doing something here, right? So when I kill here, right, the process was not expecting to go halfway through. So it may not have left itself clean, right? So it might have left some files open. We haven't seen what files are, but it might have been doing something, right? At the least, it would have been printing something on the screen, right? So it says progressing, doing this, whatever. And when it goes off, here's where you need the notion of transaction, right? So you don't want to kill, you want to abort this transaction. You want to make sure that anything that it did should be taken back, right? Not just kill it, because once it killed it, any file that it wrote is suspect, right? Because it may be using pointers, it's done halfway through. You may be lucky that it'll go through, you may be unlucky that it won't fail, right? In the rare circumstances, you would have noticed it when you have like a PowerPoint crash, gets into a deadlock or something, you kill it, and it's come back, it says file corrupt, right? How many of you seen, maybe not PowerPoint, but some application that you come back, it was doing something, you had to kill it, and it won't die, right? You have to force quit or something, or you have to reboot the machine and come back and it says, right? I think it happens a lot to Outlook Express because it uses one database, right? I have some weird cases where in Outlook, you have some mails that you sent out which are kind of in both states. It says in different state and all those things. Things kind of act up, right? And that's the notion here, because you can't just kill the process, because processes do other stuff. So you have to have so some of the mechanisms you have here are ways of which one you should kill. You can kill, choose one process, kill that, and hopefully the thing will recover, right? You can choose the one which has used the most resources and so on and so forth. But inherently, all processes are doing other stuff which we don't know what they are. So just randomly killing something would get you out of the deadlock. From the deadlock notion is fine. From an application perspective, that's a disaster, and they have to know how to get away from those stuff, right? And if you have the notion of a transaction, you can roll back. So most of the time when you come back from PowerPoint, it'll say recovering from file, and it'll go through some process and give you a new version and let you deal with that, right? So we'll start with the new module on Monday on the memory systems. And if you have any questions about the projects or assignments, talk to me. Right?